The only thing I don't like about this website is that they tell you these domain restrictions. I feel like we should have to figure these out, but I'm okay with it because the questions, like I said, are delightfully challenging. I, of course, chose the section that's on logarithmic quadratics, but it's okay. There's a whole section on sets of logarithmic equations, which are beautiful in their own right. Oh, beautiful systems of equations too. Ugh, yes, I'm loving it. So, anyways, I'll post this website because it makes me happy. The first one here, number 3, we can see again we got a number on one side. Thank you. We've got a plus in between them. Beautiful. So we could go ahead, recognize. Let's condense first. Oh, but as soon as I go to condense, when I got to remember that base, I notice, oh, wait a minute, there's a 2 here. I chose this question because I liked that nasty radical there. But if I have the 2, we know that that's going to square this whole thing, and so the radical is going to disappear. So now this question looks very, very similar to the one we had before. I'm going to have 5 minus x times this 3 minus x because the square root and the radical will cancel each other. They do add some interesting extra domain restrictions, but I mean, in fact, it's not really an issue for us because in order for this to work within the square root, it had to be greater than or equal to 0, and to work within the logarithm, it had to be greater than 0, so the logarithm has more issues with it than not. But let's see. And this is all equal to 1. And then we can rewrite using the definition of a logarithm using Barbara. 3 to the 1 is equal to, so 3 to the 1 is equal to all that stuff in the middle, right? So what is this going to be? X squared minus, I'm just doing all the math, 8x plus 15. Yeah. And so this particular quadratic, now we have a b term, right? We have the x term, so we got to set aside equal to 0. We're going to hope that this website is nice and that this factors, though, like I said, no guarantees of that in real life. It just happens most of the time in these questions. Ooh, that was a real long glitch. Good. So we get x squared minus 8x minus plus 12. All right, so 12, 6 and 2 multiply to 12 and add to 8, so we are in luck. It does factor. Like I said, this is just how life works when you're in these questions. It's like we already did enough to you. Here you go. Here's your gift. It factors. You don't have to use the quadratic formula. And then we get our answers are x is equal to 6 and x is equal to 2. Now, annoyingly, this website tells us only x is less than 3 will work, so we know the solution is this. But if we were to check our work, here's what will happen. We're going to get the log base 3 of negative 1 when we go to plug in the 6, right? 5 minus 6. And here's our issue. We cannot take logs of anything 0 or less. There's no way to raise through to a base and get out a negative number. So that one does not work. If we try the other one to check, we're going to get the log base 3 of 3 plus 2 times the log of the square root of 1, which is just the log of 1, which is 0. So we get 1 plus 0 is equal to 1, and that one does work. I did throw 4 in here just because it looked fun. This one didn't have the 2 that was going to magically save us from the square roots, so I thought it was a little exciting in that way. So if we went ahead and did our combining here, we'd have log base 8, and inside of a giant square root, because the product rule for radicals tells us that we can go ahead and combine these into a single square root because they have the same index, is equal to 1. And so then we can rewrite this. We're going to get 8 is equal to whatever this nasty square root is, because the 8 to the 1, was we rewrite with the logarithm. And then we'd square both sides. So we'd end up with 64 is equal to this whole thing. And again, they did a little too much for us, telling us all of this domain restriction. I will take some time to tell you where they got that because I do think that that's super interesting in terms of what we're doing. So let me grab this and let's talk about that domain restriction. just because it brings me joy. So I don't think I can crop it. It's fine. I'll deal with it. We want this little piece. We want to talk about where this domain restriction came from. So if we looked at the domains of each of the pieces of this, because this is two functions that are being added together, right? And we did operations on functions before. So the domain of this first one is x has to be less than 3, right? Take your 3 minus x, set it less than 0. Here's what's going to happen. The domain of this guy is that x has to be greater than 9. And so for our negative 9, way too slow. And for our both of these things to be defined, this has to be true and this has to be true. So we think about this. In fact, let me write the second one in a different color so that we can keep these things separate. Let's use red. This is x is greater than negative 9. So from negative 9 and above, but not including, right? Because it's just greater than. So we could even put our little open circle there if we want to be good about it. And above. And then for the other one, we are at 3 and everything below it. So we need both of these things to work, right? Otherwise, we can't actually add these two things together. So we call this the intersection of these two sets. And so our intersection is going to be everywhere that we have both things, our blue and our red. So the only place that these both exist is between that negative 9 and 3, which is where they're getting out this answer. And if we wanted to be cute about this and put it in interval notation, negative 9 to 3, neither of them are included in the solution set, so we'll use our parentheses. I am not going to solve that ugly quadratic that was about to happen on the other side. But my guess is it probably factors because that's fun. So that's 4.6. The only thing left we got to talk about is, I don't think I skipped anything in 4.6. Let's look back. Applied problems. Yes, so we'll do that, but that's within the models. So we'll do the solving the applied problems within our model questions, and so then we'll get to see how all of this comes together with some exponential modeling.